this video, I'm going to talk about drug metabolism and autooxidation. So my goals here are to help you understand the purpose of metabolism. That purpose is to make a drug more easily excreted from the body, typically through urine. It's also to understand how cytochrome P450, which is the most important metabolic enzyme, produces radical species as a part of these metabolic processes. We want to use our understanding of radical stability to understand metabolic patterns, because these metabolites come from stable radicals most of the time. And if we understand what radicals are stable, then we'll be able to predict possible metabolites for certain drugs. We should also be able to predict autooxidation products. So autooxidation is when molecules are oxidized by molecular oxygen, O2. And finally, we'll understand some ways in which free radicals damage cells by autooxidation and how antioxidants such as vitamins C and E mitigate this damage. So, metabolism is part of pharmacokinetics. It's what the body does to the drug, and more clearly, how the body changes the drug in order to make it more easily excreted. So this is the body breaking down compounds for elimination. Technically, we can talk about both drugs and molecules made by the body, but we'll spend most of the time talking about drugs. The liver is where most drug metabolism happens, but metabolism can happen all over the body, in the gut, the lungs, the kidneys, and even the skin. And when we think about metabolism, drug chemists often think about a first pass effect. And so we can think about some drugs cycle through the entire circulatory system several times. But even that first time, it's going to pass through the intestine, the liver, the kidney, and the gut. And much of that drug will be metabolized in that first go-around. That's called the first pass effect. When we talk about drug metabolism, we can think about two different phases. The first phase is where we're converting a compound into something more polar, a metabolite. And that's usually by making an OH group appear, either by adding it or unmasking it, making an NH to some kind of more polar functional group on the molecule. Most of the time, these metabolites are biologically inactive. They just exist to get gone. But sometimes metabolites are also bioactive, and oftentimes that's something we have to worry about. Although sometimes we can design compounds that are not bioactive until the body begins to metabolize them. That's called a prodrug. At any rate, phase 1 is going to give us these often oxidized compounds, and that might be enough to get them polar enough to go into the bloodstream easily. However, if that's not enough, then we'll engage phase 2 reactions. So phase 2 is conjugation with an endogenous substrate to further increase aqueous stability. A clearer way to say that is that we are going to staple on some piece that's very water soluble. So again, phase 1 may have made an OH group show up on our molecule. Phase 2 will take that OH group and turn it into a sulfate, or attach it to a sugar molecule, or attach it to something really water soluble so that it can be excreted earlier. We're going to focus on phase 1 reactions. There are a lot of possible phase 1 reactions, but I would say the two most important here are oxidation and dealkylation, particularly if you have ethers and amines. The most important metabolic enzyme is cytochrome P450, which is really a family of metabolic enzymes. The mechanism is a little bit complex, but we can simplify it like this. The active site of cytochrome P450 is this iron-sulfur oxo complex that you see. That can abstract a hydrogen atom from some drug, which yields a radical here and a hydroxyl on the iron compound. Now, in what's called a rebound mechanism, that OH on the iron can then be transferred to that carbon-centered radical, which gives this hydroxyl. So we're essentially replacing a hydrogen atom with an OH group. So the big question is which OH is which hydrogen is going to be abstracted? Where is this OH going to show up? That's generally dictated by both the radical stability and the enzymatic control, which is to say sometimes the enzyme will hold it in a specific shape such that a specific hydrogen will be taken. But much of the time it seems to be dictated by the stable radical. So we form a stable radical in this middle step, and then we hydroxylate it later. Most drugs have an aromatic ring, and so it's important to think about how these aromatic compounds are going to be metabolized. If there is a CH next to the aromatic ring, then cytochrome P450 will abstract that hydrogen atom and we'll get a stabilized benzyl radical, which will then be hydroxylated and converted to a benzyl alcohol. That's a good thing. What's more dangerous is when we don't have a CH next to that ring. Then cytochrome P450 will form a benzene oxide, essentially an epoxide. So on a good day, that epoxide will rearrange to give us this phenol via something called an NIH shift. It's called that because it was discovered at the National Institutes of Health. And so this phenol is a lot more polar, and that will be much more easily excreted in the urine. However, if this benzene epoxide, if this benzene oxide is intercepted by some kind of amine, by a peptide, or particularly from DNA, remember that we've talked about amines opening up epoxides in the past, and so we can get to this amino alcohol, which if this was DNA, this is an example of DNA alkylation, and this is carcinogenic. And so this is why on the bottom of the screen soot is dangerous, because the epoxides from soot can cause DNA alkylation, which can affect the cell cycle. On the top of the screen we have an example of a ring being oxidized even though there are some benzylic methyl groups there. Another way that lignocaine, which is a topical anesthetic, is metabolized is by aromatic oxidation. So here we still form that benzene oxide, but it's very quickly rearranges by an NAH shift. So aromatic oxidation is a very, very common metabolic pathway. The other very common metabolic pathway I want to discuss, actually I'll talk about these as well, anytime we can form a stabilized radical, that will be something that we'll see quite a bit. So if we give it alkenes with allylic hydrogens, we'll see allylic alcohols come from that. If we give something a ketone, we might see a radical form alpha to that. Again, both of those radicals are stabilized by resonance. And even in the absence of resonance, we've seen radical species like cytochrome P450 able to abstract a proton from an alkane, even if we can get a secondary radical like that. So we can essentially abstract most carbon hydrogens to replace them with an oxygen. But the most maybe common and easy to spot is O and N demethylation or dealkylation. So O-methyl groups, like in the top here, are very commonly seen in neurotransmitters especially. Cytochrome P450 will generate a radical next to that oxygen atom. And why is that stabilized? Well, it's kind of, I would think of it more like hyperconjugation, where my filled lone pair on oxygen overlaps my partially filled p orbital here. But this is a common radical to form, which can then take the OH from cytochrome P450 and I get this hemiacetal. And if you remember anything about hemiacetals, you might remember that they're not stable unless they're cyclic and like sugar. So this is not a cyclic hemiacetal, and so it's going to break down to give me this alcohol and formaldehyde, which will then go away. Whoops. So again, the overall reaction is losing a methyl group from a methoxy to get to this alcohol. In the same way, amines can do a similar reaction. So here I'm generating a radical next to the nitrogen. Once I hydroxylate there, I get a hemiaminal, very similar to the hemiacetal, which would then break down to lose a carbon and give me formaldehyde and give me this amine. So again, this is a demethylation reaction. My N-methyl is going away. Of course, I could also grab one of those hydrogen atoms that's on the other side of the nitrogen over here. In this case, instead of losing the methyl goes with the amine, and I'm left with a ketone, or actually I'm left with an aldehyde on the right side. Okay, So, and of course there are lots of side products here. This reversibly forms an iminium ion, which can then go on to give other products. We can also directly hydroxylate at nitrogen to get an N-hydroxy species. But I think this demethylation is a really common metabolic pathway that's easy to spot and really relevant to a lot of the compounds that you might see in your future classes, particularly if you study neuroscience. So for instance, here is the metabolism of quite a few amines of some psychoactivity. So diazepam is I think an anti-anxiety medication. So we can see that the main method for metabolism there is losing that methyl on the nitrogen to get to the NH. On the top right, this is codeine. Codeine is still used as a cough suppressant in some ways. But we can see that codeine can be metabolized to lose this methoxy, get to an OH here. This is morphine. That's right, straight morphine from the opium poppy. So keep in mind, although codeine is quite a bit safer than morphine, codeine is converted to morphine in the body. And then if you're thinking the next step of codeine is probably N-demethylation here, I think you're right. Down here, MDMA is ecstasy. This can be metabolized in a couple different ways. We can lose the methyl group on the amine to get to DHMA here. Actually, sorry, over here, this is just methamphetamine, or methylene dioxyamphetamine, this thing. Right, so I lost the CH3 on this amine. I can also lose the CH2 between these oxygens here. It's called demethylation. And get to this dihydroxy methamphetamine. Down here, methamphetamine itself can also be metabolized a couple different ways. We talked about aromatic oxidation earlier, so we can end up with 4-hydroxylation, again probably through the benzene oxide. It's more common though that methamphetamine undergoes demethylation to give amphetamine. We chop out the methyl group here. And then the next step would be chopping off the other side of the nitrogen to give this ketone. This is a different enzyme, and this is more catabolism than metabolism. But monoamine oxide is another metabolic enzyme. It's meant to break down monoamine neurotransmitters like serotonin. So this is an early antidepressant drug target. The idea was that depression is associated with lower levels of serotonin in the brain, and so if we can slow down the rate at which our body tears up serotonin, we can keep serotonin around longer. And so that's why MAO inhibitors, or MAOIs, are found early use as antidepressants. And this is the general thinking. Again, the mechanism is similar to cytochrome P450, where we're going to chop this carbon-nitrogen bond and end up with an oxidized metabolite. So one powerful oxidant that we see every day is oxygen. When molecular oxygen acts as an oxidant, we call that autooxidation. So one thing we need to remember about molecular oxygen is that it's actually a triplet ground state. So there is not really a double bond. Those electrons are unpaired. And so dioxygen essentially acts like a diradical. And it is reactive like a diradical, right? That's why oxygen is so reactive in general. For instance, that's why if you fill your tires with nitrogen, it'll last longer than if you fill your tires with oxygen, because oxygen slowly will chew up rubber. Anyways, one important example of autooxidation is with THF. So that's tetrahydrofuran. This is a really common solvent. It's an ether. So if we have any kind of radical species around, again, which might even just include oxygen itself, we can abstract a hydrogen atom next to oxygen, much like we did on the earlier slide. But that radical can also just add to oxygen, and that gives this peroxy radical. That peroxy radical can take a hydrogen atom from another molecule of THF. This is now a chain reaction because we regenerate some of this radical, and our product is this explosive peroxide that's actually shock sensitive, so you have to be very careful with it. And so the upshot of this is that anybody that ever uses THF or any other ether has to really make sure that oxygen isn't getting into that system, and that we date the bottles and regularly check ether bottles for peroxide formation. Another important example of autooxidation is lipid autooxidation. So lipids are often unsaturated fatty acids. These are very important in cell membranes. So if you notice, there's two double bonds here, but these double bonds are not conjugated. There's actually a CH2 between them. And so some initiator, which is usually some form of reactive oxygen species, peroxide, hydroxyl radicals, superoxide, some radical initiator can take that hydrogen atom, and now we have a delocalized radical. That radical is delocalized over 5 carbons. Much like before, that can add to gaseous or diatomic oxygen, and we'll get this peroxy radical, which again carries out continues the chain reaction by grabbing a hydrogen atom from some other molecule of fatty acid. And then the product of this, thankfully, isn't quite so explosive. But what we've done is taken the nonpolar end of our fatty acid and made it significantly more polar, right? That OH is now an extra hydrogen bond donor and acceptor. So what does that matter? So these fatty acids are important in cell membranes. If you think about the structure of a cell membrane, you've got these nonpolar tails kind of self-organizing here, and you've got these polar heads over here. What happens when we do this autooxidation in the middle of a chain is that now we've got a polar part. And that polar part wants to go migrate to be with the other polar parts. And that's going to really hurt the integrity of our cell membrane. So we would like to have some way to mitigate this kind of autooxidation. And so one way to do that is an antioxidant. So antioxidants are essentially set up to more or less easily lose a hydrogen atom to some kind of free radical like reactive oxygen species. All right? And the idea here is that we're making a radical that's so stable, stabilized by resonance, that the chain reaction is essentially broken because that radical will just sit there. So for instance, ascorbic acid, vitamin C, very common radical trap. If it loses that OH that I've circled in green, if it loses that hydrogen atom on the oxygen, then that radical on oxygen can be delocalized all the way across that system. I know I said that OH bonds are usually too strong for this, but that conjugation available to the radical makes that OH bond a little bit weaker. On the right, we've got vitamin E. So the tocopherols are lipophilic. So this is fat soluble. This is going to be more relevant to the non-polar tails that we're looking at here. But here, vitamin E can lose that OH and give us a radical that can be delocalized through that whole ring. To summarize, drug metabolism is when drugs are made more polar and water soluble by the body to aid in their excretion. The most important metabolic enzyme is cytochrome P450, which works by a radical mechanism to abstract hydrogens from compounds to form relatively stable radicals, which it then oxidizes or hydroxylates. Aromatic compounds form epoxides or arene oxides, which can then NIH shift to relatively harmless phenols, or can be opened by DNA, which can cause DNA alkylation and tumor promotion. Ethers and alkylated amines can be dealkylated or demethylated. This is very common in the metabolism of psychotropic drugs. Autooxidation is when radical intermediates, such as the kind we talked about in metabolism, can react with dioxygen to form hydroperoxides. When this happens with lipids, it can disrupt cell membranes. And so sometimes we take antioxidants to try and mitigate some of this damage. Antioxidants interrupt the chain reaction by forming stable radicals when they come across free radicals.